All right, welcome back. In this video, we're actually going to look at the math. So let's dive in. We want to solve the household problem. And so we need to write down an intratemporal utility function. Let's just use, for variety, let's look at log utility. So log consumption. And we will take the usual CRA specification for labor. So this is a case we looked at in TD1s. One other parameter that you see sometimes in papers, and this included, is theta here. So this will be a distaste parameter. This is going to be distaste for labor. So when this is not here, you can think that it equals 1, but this is a free parameter that lets us scale how much agents in our economy don't like to work. So you can think that if theta is larger than 1, then the penalty term here in their utility for working gets bigger. So let's have a try at this one. You should also know that there's a connection between log utility and the CRA function, that if you look at our normal ct to the 1 minus sigma c divided by 1 minus sigma c, and you solve for the limit as sigma c goes to 1, then this will be equal to the log of sigma c. And this is a nice math exercise that, of course, you don't have to do, but it's nice to know that these have this equivalence. The same equivalence exists between the CES production function and the Cobb-Douglas production function. The Cobb-Douglas production function is a CES in the case where the elasticities of substitution go to 1 in the limit. Okay, just enough of that sidebar. So this will be our intratemporal utility function. And our budget constraint will be as normal, that the household will consume and invest. And they will consume and invest by getting money from capital investments based on their last period capital and wages from the current period. And they'll also receive the profits of the firm. This is a term I drop sometimes, the firm profits here. It's quite sloppy that I drop this. I do it because it does not appear in any first order conditions. But you should include it for completeness. And in fact, this term allows you to get to y equals c plus I, the whole resource constraint for the entire economy, without ever writing down y equals c plus I. You can see that if you were to plug in the equation for profits, that profits are equal to the amount produced, YT, minus the total costs, which is going to be RT, KT, minus WT, LT. You can see right away if you put this here, this and this cancel, this and this cancel, and you just get YT is equal to CT plus IT. So the profits are important for closing the economic system in theory, but in practice, because when you take first order conditions for the household, there will be nothing that involves profits, you don't really have to worry about it. But let's make sure to include it to be complete. The household is also subject to the intertemporal, the law of motion of capital, kt plus 1, which is going to be 1 minus delta kt. And now we're going to include our phi function, which was 1 minus gamma over 2, 1 minus it over it minus 1 squared times it. Okay, so this is now the household problem. And I apologize, I wrote this backwards. So I guess it doesn't matter because it's a square. I'll just leave it like that. In my notes, I had it written like this, it over it minus 1 minus 1. But because we're squaring it, it doesn't matter the order that you put them in, right? It's a symmetric function. But I'll write it correctly to match my notes. So it over it minus 1 minus 1. Okay. And now we need to maximize. So remember, the households problem is to maximize. We've written down a 1 period problem. We want to maximize the total discounted stream, the expectation at time t, the total discounted stream for all periods in the future, beta s u t plus s, subject to a series of budget constraints, one for each period, subject to 1, let's call this 1, let's call this 2, so subject to 1 t plus s and 2 t plus s. And we're going to do that by choosing CT, KT plus 1, LT, and IT. Remember that normally we would like to, whenever you're facing a constrained optimization problem, you want to look through your controls and ask yourself, can any of these be eliminated just by substitution of the constraints? So normally we would take the KT plus 1 equation, we would solve it for IT, and we would plug it into the first constraint. So we would go from 2 constraints to just 1 constraint, and then we would be able to eliminate a control. So we would go from having to solve a 2 constraint optimization problem of 4 controls to a 1 constraint optimization problem of 3 controls. You should see that in this case we cannot do that because we have a cubic function in IT. Right? If you multiply this out, it's square, and then you multiply by IT again, so you have a cubic function in IT. We can't just solve for 1 IT. So you have to solve this as a 2 constraint problem with 4 controls. Okay, so your job now is to write down the Lagrangian, and I will do that as well, and I'll see you in the next video.